into the non-Mendelian inheritance. So yesterday, as I told you, the laws of Mendel. Okay, so mostly, universally, all the genes, they follow Mendelian inheritance. So they obey. So when there is a Mendelian inheritance, so we can usually guess the ratio. Okay, like as I told you, 3:1, then 1:2:1, like that, whatever for the monohybrid cross. And for the dihybrid cross, 9:3:3:1. So all this, yesterday, I showed you how to calculate. That you have to practice. Then some inheritance, some types of inheritance, they are not obeying that ratio. We are getting a different ratio. Such kind of inheritance is called as non-Mendelian inheritance. So here, in the Mendelian inheritance, the process of genetic transmission from parents to offspring, it is called the inheritance. So it is a sum of characters which are genetically transmitted from parent to offspring. And here there are two laws, principle of segregation and law of independent assortment. So that means the alleles are segregated into each gamete and they are independently assorted. That means the segregation of one allele of one gene is not affected or influenced by the other gene. Okay, that is what we have discussed yesterday. So in the non-Mendelian inheritance, most pairings lead to offspring with genotype and phenotype ratio which have not matched the Mendel's laws. So such kind of deviations are called non-Mendelian inheritance. So there are two natural deviations. One thing is Mendel's laws are not applicable for all. So both genotypic and phenotypic ratio have like variations. Then genotypic ratio is that expected from Mendel's laws, but phenotypic ratio is not. So that means, as I told you, like incomplete dominance and codominance. So in such cases, genotypic ratio is correct. It is matching the Mendel's laws. But phenotype, if we see, the capital is giving red color. Smaller is giving white color. So according to Mendel, capital smaller also should give red color. So we will get 3:1 ratio. But here, because of incomplete dominance, what happens? Capital is giving red color, capital smaller is giving pink color, and smaller is giving white color. So here the phenotypic ratio has changed. So such kind of variations are called non-Mendelian inheritance. So yeah, just now what I'm telling, incomplete dominance. So in this type of non-Mendelian inheritance, so the genotypic ratios are as expected of the Mendel's laws because capital will be 1, capital smaller will be 2, and smaller will be 3, 1. So 1:2:1 ratio, genotypic ratio is correct. It is matching. Whereas phenotypic ratio, it is like 1:2:1 again. So 1 red, 2 pink, and 1 white. So this is because of incomplete dominance. That means the R, capital R is not completely dominant over the small r. Right? Then codominance. So I told you yesterday about the blood grouping. So codominance is where the both alleles express equally. They're not dominating each other. So in that case, we have A blood group, B, AB, and O, right? So that means both are dominant, equally dominant. So in such case also, you suppose if you see, there is, yeah. So this is one example, okay? That is a blood group. And another example, I will show you with the ratios, so that will be good. So here, another example, this is a dihybrid cross where codominance is that of the coloration of the rhododendron flowers. So here the homozygous dominant gene pair gives rise to red phenotype. That means both should be dominant. Then only we will get the red color. That is AA, capital A, capital A, capital R, capital R. If one is dominant and other is heterozygous, that is capital A, but R, capital R, small r, which is heterozygous, it is giving pink color. So you can see the coloration in the table. So that means here both are dominating, and in a heterozygous state, you are getting a different color. So in such cases, what happens is the genotypic ratio remains same, but phenotypic ratio will alter. Then another aspect is multiple alleles or polygenic inheritance. So here, till now we have discussed only two alleles. Okay, either capital R, small r, or capital Y, small y, capital W, small w, or like that. That means one dominant, one recessive. But this is with that, like when a single trait is controlled by a single gene or single allele. So in such cases, you can see only two alleles. But if a single trait is controlled by multiple alleles, then we will have many possibilities of alleles and also many possibilities of phenotypes. So, and one more thing is the environmental factors also influence. That is the photo period and duration of day. So that means how much time the plant is exposed to the light and duration of day. So in some case, some countries, we see that the day will be longer than night, and in some seasons also. So in summers, usually we see that the day will be longer, and in winters, the nights will be longer, right? So based on the like seasons, countries, so everything, these alleles and their expressions will alter. So some common examples of this type of inheritance is human blood groups, as discussed yesterday also, and height and eye color in humans, and fur color in animals. So anyway, we will discuss some examples here. Yeah, so this is the skin color. Okay, so we all know that color is because of pigmentation, that is melanin. So melanin pigmentation causes the color. Okay, so in those people who belong to the countries where there is a more exposure to the sun, or those people who are based on their work, so they are more exposed to sun. So in them, more melanin production can be seen than in those people who are less exposed to sunlight. Okay, so when you see this skin color, it is not just like fair or dark. It is many like what you call many shades can be seen. Wheatish, not completely dark. So it is in between, not completely fair. Okay, so many types of skin colors can be seen across the world. So this is all because of the multiple alleles which are contributing to the skin color. So like this. So that means it is a continuous. Discontinuous means there are two types of data, continuous and discontinuous. So discontinuous data means only two options. It will give a peak, single peak. But in continuous data, it is not a single peak because lot of variations, a lot of ranges can be seen, okay, within the people or population. So this is one of the examples, okay. So in such cases, we call that as a continuous data. Like so for another example, suppose if you take hemoglobin, it is not just 12 or another number. No, some will have 5, some will have 6, some will have 7, some will have 8, 9, 10, 11, 12, 13, 14. Like that, the hemoglobin percentage will vary. So in every percentage, there will be people who are having that percentage of hemoglobin. So it's such kind of data is called continuous data. And another one is BMI, body mass index. So it is not that only the people who are having 20 or 24 or 22. No, some will have 20, 18, 19, 20, 21, 22, 23, like that. So such kind of data are the examples of the continuous data. Then linked traits. So linked traits are nothing but, so I told you yesterday that the inheritance of one gene is not influenced by the inheritance of other gene. So alleles in one gene with that of alleles in another gene. But in linkage, usually the genes are linked. That means the inheritance of one gene is, it influences. That means if A capital A small a or capital A are the alleles of one gene, and capital B small b or capital B are the alleles of the other gene. So if capital A is inheriting, definitely if it is linked to capital B only will come. So are you getting? So that means in one gene, if it is independent assortment, then if capital A is getting inherited, then there is a chance that either capital B can inherit or small b can inherit. So you will get two combinations, capital A, capital B, capital A, small b. This is in independent assortment. But in linkage, what you can see, if one allele is coming, suppose A and B, capital A and capital B are linked. Then if capital A is coming, inherited to the offspring, then definitely capital B only will come from the second gene. It is not the small b. So only one combination you will get, capital A, capital B. So this is called as linkage. So genetic linkage is defined as a tendency of DNA sequences that are close together on a single chromosome. They inherit together in the meiosis phase. Okay. So like red color, fair skin, wrinkles in the humors, these are the combinations. That means all the three, suppose the people who have fair skin, usually you don't see black hair, right? Red hair will be seen in those people. And freckles will be seen on those. Freckles are nothing but like small dots on the face. Okay. So in human beings, like these three genes are linked. Okay. So this is the example. So how this sex-linked traits means? So see, in the same chromosome, there's gene 1 and gene 2. If they are linked, they will pass together. If that chromosome is passed, so the genes also, gene 1 and gene 2 will be passed as it is. If they are present on different chromosomes, so the small one is Y chromosome and large one is X chromosome. So if they are on the two different genes, then they won't be linked. And you see in the third image, even when they are present in the same chromosome, but if they are far away, then also there is a chance of no linkage. Okay. So yesterday I told you about hemophilia. So let me explain you here. So the inheritance of hemophilia is a very good example of sex-linked inheritance. So it is a recessive sex-linked trait that affects only males, while females in the family are the carriers of the disease. Yesterday I told you about Victoria, Queen Victoria and her descendants. So it's a recessive. Okay, that means both the copies should be present. Only then it will express. Right? If only one copy is present, it won't express. This is because the gene that encodes the hemophilia is present only on the X chromosome. In heterozygous females, that means in females, there will be two X chromosomes. So heterozygous means if this gene, hemophilia gene is present on one X chromosome, but not present on the another X chromosome, because it is recessive. So one chromosome is normal. Another chromosome is having this gene. So as it is recessive, even though like it is present, as one normal chromosome is present, also present, usually they won't get this disease. Okay. And they won't express this disease, but they are carriers. Okay. So normal X chromosome will be expressed. Whereas in males with X chromosome, the disorder will be expressed as in males we see X and Y chromosome. Okay. So even if this is recessive, but still only one X chromosome is there here, there is no another X chromosome to compensate this gene. So definitely the genes present on the X chromosome will express, because there is no normal gene in them, right? So therefore, hemophilia is passed. So though it is present in the females, they are carriers only because they have normal X gene. So X chromosome, a normal gene is present on the X chromosome. Whereas in the males, as this defective gene is present and there is no normal gene to compensate, definitely they will have this kind of disease. Okay. So this is how it looks like. See, father is having XY, mother is having XX. So from father is having this disease, suppose. So one X from father, one X from mother, XX, female child. Then suppose another child is there. So one X comes from mother, Y comes from father. Then similarly, you have another two children. So in this in female children, though one defective gene is there, there is another normal gene also. So usually they are carriers of hemophilia. But if the defect is in the mother, so suppose you see this female child who is having XX, one is defective and one is normal. When she marries another normal person, and then in the next generation, what happens? This female child is having XX, one defective gene, and she married a healthy person who is having XY. Now they have 4 children, suppose. So son is getting healthy X gene, normal X chromosome from mother and Y chromosome from father. So he is healthy. So daughter, she is getting defective X chromosome and another X chromosome from father. So still she is also healthy, but she is carrier. But this son, second son, he got this defective chromosome from mother and Y chromosome from father. So definitely there is no healthy gene in him. So definitely he will get the hemophilia. And another daughter, she got normal X chromosomes from father and mother. So she is healthy. So here out of 4 children, 2 are healthy completely. One is carrier and other is affected. Okay, this is how the inheritance looks like.
Ma'am, after 4 children, if the 5th or 6th will there, so they are also affected.
Yeah, definitely. It is like 4 in the sense I am telling like 1/4. 1/4 of the children.
Okay.
Don't go with the number. Suppose this is 100%. You can see 1/4, like half of the children will be healthy. As 2 children are healthy, you can just calculate like that. 50% will be chance of having healthy children. So another 50%, 25% if female and she is getting the diseased gene, then she might be carrier. And suppose it is not 100% that one of the male child should get defective gene. So that is also we cannot say for sure. Okay, suppose in case he is getting the defective gene, definitely he will get affected. Okay, so there is a 25% chance that male child will be affected. Right?
Yes, ma'am.
Okay. So here, this is the case study, what you say, that so Queen Victoria and Edward, so they had, Victoria and Edward, they have Queen Victoria she married Albert. So this Queen Victoria, she is carrier. Okay, carrier female. Then again, out of her children, Elise, she is again carrier female. But what is the name? Leopold. So he was hemophilic male. So that means one of the children. So he got affected. So if you see in this family tree, only male children. So they have got affected. So why this is so important? Why we are always taking Queen Victoria's example? Because a lot of people will get affected. Not only her family, but many families. Here is why it is so prominent is that because
Ma'am, your voice is not coming properly.
Okay, now is it clear?
Yes, ma'am.
Okay. So why this case study only we are discussing multiple times? Because actually this has changed the history. So because of that Alex who got this hemophilia, he was prince. So he was descendant of Queen Victoria. So he got this hemophilia. So at that time there was no knowledge about this disease and all these things. So he got some cut and there was the bleeding has not stopped. So then the parents realized that, okay, so you should be very careful. Okay. So then they have protected the child for longer periods of time. But later there was some revolution, okay, from public revolution or something. So during that time, so this disease, actually the people came to know, I don't know exactly the people or some rivals. So they came to know that this boy has this disease. So using this disease, so they have actually killed him. And also because of this disease, actually the father couldn't concentrate on the country and all these. So because of that, the complete kingdom has lost its power. So something like that happened. So the history has changed because of this disease. Okay, so that powerful a single gene is. So that is why we are repeatedly discussing this case study. So it is very popular. Okay. So this is about the
now that disease is not having any any cure, any medicine
No,
treatment.
at that point of then no, but now also it is only the gene therapy. So genetic diseases, we don't have any treatment as such. The only thing is management.
Okay.
So we can manage that if possible through diet or whatever. Means it depends on the phenotype, what actually that disease is causing. I will also discuss one or two inborn errors. So there I will explain you. So
Okay.
how can we do? So in brief, I will just explain linkage and crossing over also. So as per, I told you, like one allele is dominant of the other if two alleles are there. So all traits are monogenic. If that means a single gene is controlling the trait, then in such cases, each gene will have two alleles. So this is a normal perception. Okay, exceptions are there. But normally, a trait or a character is controlled by a single gene where it has two alleles. So these two alleles, one is dominant and other is recessive. So all chromosomes occurs in pairs and the genes will assort independently. So I am not repeating again. Independent assortment. Okay. So linkage. So William Bateson and Punnett, they were working on several traits and later they could find that there is linkage. Okay. A gene for purple versus red flowers and a gene for long pollen grains versus round pollen grains. So they were like dihybrid. So 2 genes they were actually studying. So in that, they didn't get the expected ratio. Okay, they got different ratio. So you can see after they crossed capital P, capital P, capital A, capital, that is pure form with that of pure recessive form. So actually they should get pure long 284, but they got 215. Sorry, they got 284, but expected number is 215 only. So like that they have got differences in the number. So then they actually thought why we are getting different numbers, different ratios. So this is because of the linkage. Then they have done test cross. So test cross also I have told you yesterday. So here they after test cross, they expected, I told you 1:1 we should get. So here there are 2 genes. So 1:1:1:1 ratio of phenotype should get. But they got 7:1:1:7. So here also it has changed. So this is because the parental phenotypes reappeared more frequently than the expected. So because if it is independent assortment, so only 50% of the cases you should get parental. Other 50% will be recombinant. Recombinant in the sense there will be combinations. But here parental genotypes and phenotypes are reappearing more frequently. This is because they are not independently assorting. Okay, there is some deviation. Then they came to know that there is something wrong. Something is happening. Some deviation is there. Then Thomas Hunt Morgan, actually he did experiment and he came with the concept of linkage or coupling, and he explained the concept. In the Morgan's experiment, he performed experiment on Drosophila, that is fruit fly. So both the white eye gene, capital W, and a gene for miniature wings, M, are on the X chromosome. Okay. So in 1911, so the Morgan, he crossed a female with white with wild type male. So in the F1 generation, so he could see that white-eyed with miniature wings. All males are white-eyed with miniature wings, and females were wild type. Okay. So like this you can see. So females are white-eyed miniature wings, and males are wild type. But in the next generation, F1 generation, so males got wild type and females got white eyes and miniature wings. So then he could see in the F2 generation crossing, so he could get different type of combinations than the other, like what the expected ratio. Okay. Then he came up, no need to remember the experiment. This is for understanding only. Then he came to know about the concept of linkage. So linkage is defined that a failure to independent assort independently. Okay, that is the 2 genes which occur very close on the same chromosome, they assort together or they inherit together. Okay. So crossing over can occur in the prophase of meiosis 1. I told you in the cell division. So the homologous chromosomes, they break at identical positions and they rejoin. So that is called crossing over. So in that we will get different combinations.
Ma'am, what is the difference between linkage and crossing over?
Linkage means it is a normal process. The crossing over means we will get hybrid varieties. So linkage here means, suppose, as I told, I will just give you one example. Normally, if suppose father is tall, having straight hair. Mother is short, curly hair. These are 2 genes. Hair type, that is straight or curly, is one gene, and height is another gene. Okay, in normal if it is, if there is no linkage, so how it has to happen that of course they are, suppose they are having 4 children. So one will have tall, straight hair, 2 will have tall, curly hair, and third person, the fourth child should have short, curly hair. So this is the combination, right? So according to Mendel. But this is independent assortment. That means the hairstyle, that is whether it is straight or curly, has nothing to do with the height. So tall people can have straight hair or curly hair. Short people also can have straight hair or curly hair, because these two are independent. That is what the independent assortment is. But if it is linkage, if the 2 genes are linked, then definitely these tall people, they will definitely get only straight hair. And short people, they will only get curly hair. Is it clear?
Yes, ma'am.
So that linkage means they are linked. If one is coming, then definitely the phenotype or the allele of the other gene, you can expect what kind of allele is also transmitted. So that is called linkage. In the cross, this is a normal process. See, in the chromosome, when the genes are located very close, they fail to assort independently, so they come together. So it is nothing to do with any, we don't find any hybrid varieties here. But in the crossing over, suppose I will, if image is there, I will show you. Wait. Yeah. So here you can see crossing over means here you have 2 chromosomes, right? So here, these green ones and red ones are there on the blue chromosome. Pink and light green ones are there on the yellow chromosome. So that is how they have to inherit. So in the linkage, what happens? This green and red, if they are very close, you will get only when red is transmitted, even green will transmit. That is what we are discussing. But in crossing over, see, this blue arm of one chromosome is crossed with the yellow arm. Now you see after reunion, now on blue chromosome, you have 2 copies of green genes and 1 copy of red gene and 1 copy of pink gene. So it is completely of different combination, right? Is it clear?
Yes, ma'am. In crossing over, we get the variety, but in linkage, we get the same only.
Yes, true. So that means, because why we are different from our parents? That is because of this crossing over and recombination.
Ma'am, linkages occur in our system also.
Yeah, in humans also we see linked genes. So usually diseased
Okay,
genes.
like some. Okay.
I mean not diseased genes. So genes with some alleles. So when we do research on that, so we usually see that suppose if the 2 genes are linked, then if there is mutation or some, I mean polymorphism is there in one gene, definitely the other gene also will influence that particular disease or something, protein expression or like that. And one more thing is linkage or crossing over, they don't cause any diseases, they are not any mutations or anything. But the thing is, the phenotype, what it is, suppose first gene is expressing some enzyme, and second gene expressing some enzyme, then if there is any change in one enzyme, then definitely it will influence the change in the other enzyme. So that is what, if we go in depth, you can see some examples on that. So even in human beings also we see. Okay.
Okay. Okay.
Okay. So this is what is crossing over is. So, and this is the recombination process. How the recombination occurs is, see, this is the double-stranded DNA from mom and DNA from father. So here blue and red. Red is from mother and blue is from father. So here, how this recombination process occurs is, there will be a cut in the one chromosome of the mother and one chromosome of the father. And there will be crossing over here. Then after that, again the ligation takes place. That is these are all like, there are various enzymes, ligases, then polymerases, which will do all these things. So finally, what we are getting, half segment is from the father and half segment is from the mother. So now we get different combination of genes. So when we get different combinations, we look usually in between we will have the characters in between the mother and father, not completely identical to either mother or father, right? So every child, they vary from their parents, right? So this is called as recombination process, and this is because of this crossing over. Okay. So yeah, no linkage independent assortment. So now I will just stop this here, and then I will show you the inborn errors, because time won't permit.
Yes, ma'am. You can go directly to the diseases, ma'am. I know the
Yeah.
what we call it, description or definition of that.
Yes.
You only explain that
Yeah.
diseases.
Yes. Yes. So I will just discuss how many of I can explain. I will explain you. So inborn errors of metabolism is nothing but, so they are genetic diseases, so which are influencing the metabolism. Okay. So the metabolism includes various enzymes. So anabolism and catabolism, we know that, like breakdown and synthesis. So they have various enzymes. At every step of this pathway, we'll have enzymes. So these enzymes are coded by various genes. So when there is a defect in the gene, so that enzyme will affect, and that enzyme, if it is not present, the pathway will get affected, and the phenotype will be something change in the pathway. Okay. The inborn errors of metabolism it's a genetic diseases where the like substrates or enzymes, usually enzymes will alter. And when the enzyme is altered, then the substrate cannot get converted to product. So the normal function is disturbed, and we will get disturbed phenotype. So inborn errors of metabolism are referred to as inherited metabolic diseases or congenital metabolic disorders. That means by birth, we usually get. Okay. So this is Gerard's hypothesis. So substrate A is getting converted to B, and B is converted to C. So when there is enzyme which is converting B to C that is defective, then that pathway will be closed, stops, and this B will convert to D instead of C. During that point of time, this D will be toxic. So that will adversely affect the children. So major categories of inherited metabolic disorders are, so disorders involving carbohydrate metabolism, amino acid metabolism, organic acid metabolism, fatty acid oxidation and mitochondrial metabolism, porphyrin metabolism, urine or pyrimidine metabolism, steroid metabolism, mitochondrial function, peroxisomal function, lysosomal storage disorders. So these are various categories which are important metabolism. So first we will discuss about the carbohydrate metabolism. Let me check. The most important means, I will tell you about amino acid metabolism, and because that is most important. Glycogen storage. Yeah. So here the most very popular one, very important one is phenylketonuria. So phenylketonuria is an autosomal recessive metabolic genetic disorder. So phenylketonuria here, it is autosomal. That is, it is present on the somatic chromosomes, and they have recessive. Means if both the copies are present, only then the gene is, the phenotype is expressed. So it is mainly for the deficiency in the hepatic enzyme that is in the liver. That is phenylalanine hydroxylase. This enzyme metabolizes phenylalanine to tyrosine. So you know amino acids, right?
Yes, ma'am.
Okay. So from phenylalanine to tyrosine, that metabolism is affected here. So when this enzyme is deficient, this phenylalanine gets accumulated and it gets converted into phenyl pyruvate in the urine. You can detect in the urine. So this causes the problems in the brain development, causes mental retardation, brain damage, and seizures. And here the treatment is we can reduce the levels of this phenyl pyruvate in the blood. Okay, only that we can do through diet and cognitive development. So it is usually detected in the HPLC after birth. So it is very important. So by taking this opportunity, I would like to convey that newborn screening is very important. Though it is not made compulsory in India, in other countries, so they will do this newborn screenings. Even in India, now we have got many like companies who are doing this. We are getting kits even in the hospitals if we can actually perform that. So this is very important. Like very common diseases, we can actually screen. Why I am telling newborn screening? If the child is having this kind of error, definitely it will they will express the phenotype after 1 year or 2 years. But if we know as early as possible, we can actually include them in the diet. We can take proper precautions. Suppose if we don't know, suppose one child is having phenylketonuria, we don't know. So what we are doing, we are feeding them with the food having phenylalanine. Then what happens? Already the child is getting accumulation of phenylalanine, and again we are giving the diet with phenylalanine, and then what happens? The disease progression will be more fast, right? So that's why newborn screening is very essential for the children. So signs and symptoms are seizures, albinism, musty odor, okay, in the baby sweat. Then urine also will become musty odor, okay. So the treatment for this is we can manage the levels only through medication and diet. We cannot change the gene. So they will have special diet, which is low in phenylalanine, at least in the first 16 years of their lives. Complete restriction. It is not, no cheating, okay, complete restriction. So eliminating foods high in phenylalanine, such as meat, chicken, fish, eggs, nuts, cheese, legumes, cow milk, and other dairy products, starchy foods, okay? And they should be monitored in the, like with the doctor. So infants require a commercial formula milk that is free from the phenylalanine. So tyrosine is normally derived from the phenylalanine. So, but here it is not happening. So it has to be fed in the food. So sweetener of aspartame must be avoided, okay, because it is having 2 amino acids, phenylalanine and aspartic acid. And oral administration of tetrahydrobioprotein can reduce the blood levels of the amino acids in patients. So for childhood, we have to add, excuse me, we have to add some fruits, vegetables, which are low in phenylalanine, but provides minerals and vitamins. Okay. So this is the list of the foods which are phenylalanine free. Then maple syrup urine disease. So these amino acid disorders, that is protein disorders, are very important. Okay. So they are called branched chain ketoaciduria. So it is also autosomal recessive metabolic disorders of branched chain amino acids. So here it is caused due to the deficiency of branched chain alpha keto acid dehydrogenase complex leading to the leucine, isoleucine, valine, etc., which are toxic. And the toxic byproducts, they accumulate in the blood and urine. So they produce maple syrup. I think you might know this maple syrup, syrup of maple fruit. So it will be sweet, okay? So the urine of these patients will get the sweet smelling urine, and the odor is similar to that of maple syrup. So their children look healthy, but later their brain will damage and eventually die. So early infancy, we have to look for the symptoms where poor feeding, vomiting, dehydration, lethargy, seizures, hypoglycemia, ketoacidosis, pancreatitis, coma, and neurological decline. So these are the symptoms. Management is careful monitoring of the blood chemistry and
disorder.
yeah? Sorry.
It is protein disorder.
Yes. That is amino acid disorders.
Okay. But we are having phenylketonuria, Alkaptonuria, albinism, and trianosis, ma'am. That is not
okay,
the...
Okay. I will just explain. So this is also another important one. Okay, I can skip it, no problem. So even that is careful monitoring and special diet is important. So what is the another one? Alkaptonuria.
Yes, ma'am. Alkaptonuria.
Yeah. So alkaptonuria is called black urine disease. So it's a rare inherited genetic disease of phenylalanine and tyrosine metabolism. So this is an autosomal recessive condition. It is also defect of homogentisate 1,2 dioxygenase. So actually this participates in the degradation of tyrosine. When this is defective, so toxic tyrosine byproduct, that is homogentisic acid, get accumulated, that is alkapton. This accumulates in the blood and excreted in the urea. So when this urine exposes to the air, so usually that will convert into black color. So excessive homogentisic acid cause damage to cartilage, heart valves, and even precipitated as in the form of kidney stones. So there is no treatment modality is there for this. Only treatment is dietary restriction of phenylalanine and tyrosine and large doses of ascorbic acid, that is vitamin C. So in children, we can actually manage, but in adults, we don't see any such kind of management also. What is the another one?
Albinism.
Albinism.
Yes.
And one more thing is?
Tyrosinosis. And Gotiros cretinism. Over, ma'am. Then we are having one gene and one enzyme theory.
Okay, just I will check if it is there in the slides. Okay, I think those two are not there in the slides. So because I don't have all the specification of the genes, anyway, you can just, these two are most important. Okay, whatever this, you might get questions also from such kind of like phenylalanine and this is phenylketonuria and alkaptonuria. So you can just text me the topics in the group. If I find the notes, slides I will share. Okay.
Okay, ma'am.
So, okay. So you came to know like what is the metabolic disorders. So that means if the enzyme which is involved in some metabolism, if it is defective, then that particular metabolism will be affected. Okay, that is what the metabolic disorders. Then the concept of gene. Okay, one gene, one enzyme, right? So,
Yes, ma'am.
So this is Beadle and Totem. Actually, they have given this concept, one gene, one enzyme in 1942. So when they were performing experimentation on bread mold Neurospora. So this Neurospora crassa, this will usually grow in minimal media. Means it doesn't require any sophisticated, even minimal media also we can see. And it synthesizes metabolism. So if the biosynthesis is under control, then these mutant of genes actually require additional metabolism. That means, see, suppose gene A is coding for some enzyme A, small a, okay? If this is controlled by a single gene or one enzyme, then suppose if that enzyme is defective, suppose as I told you, if phenylalanine to tyrosine, that is controlled by one enzyme. If that enzyme is defective, then what we are doing, we are giving this tyrosine in the food. So in the same way, we have to supplement that metabolism in the media for neurospore. So what this Beadle and Totem has done is, they have actually selected each and every gene, they have exposed them to some light, irradiation, and they have actually prepared mutants, and they found like each gene is coding for one enzyme, and this enzyme regulates that particular step of the metabolism. But later, one gene, one polypeptide hypothesis came, because it is not always the enzyme. Not everything is not enzyme, right? So polypeptide is nothing but it is a smaller version of the protein. Okay, so all enzymes are proteins, but even RNA enzymes are also now discovered, ribozyme, which is of like RNA origin, but not protein. So in such case, you should not call that as one gene, one enzyme. So here you can see that precursor is giving some ornithine. Gene A provides enzyme A. This ornithine gives citrulline. So where gene B gives enzyme B, and citrulline to arginine, where gene C is giving enzyme C. Although it is an enzyme, we should call it as a polypeptide. Okay. So these are the two concepts: one gene, one enzyme, and one gene, one polypeptide. Is it clear?
Yes, ma'am. Ma'am, it is important.
Okay.
Gene and one enzyme theory.
Yeah, maybe for short questions you may expect.
Okay.
Okay. Yeah, I will share all the slides last week's and to this week's in the group, and also important questions you have asked. No? So once can you post like the index of your textbook in the group
Index of?
with subtop?
Okay.
What are the topics? What is your
Okay, ma'am.
syllabus? Okay.
I will take the photo and share in
Of
the
this
group.
paper. Yeah. Okay. I will
From
check
the
once and then I will. Sorry.
We are having from the 4th block, ma'am, evolution.
Okay.
Unit 10, origin of life and introduction to evolutionary theories. Lamarckism and Darwinism is there. And unit 11, we are having types of fossils, dating of fossils, evolution of man, and
Yeah, that I have. Like, I mean, side headings. Like, if there are, like, suppose genetic disorders. So, what are the side headings? Like that.
okay,
If
ma'am.
there's
But
detailed index is there, you just keep the picture of that.
yes, ma'am, I will share. But 4th block is left now, ma'am. So from the 4th block, you can say which one is the important.
Okay, yeah, I will share you in the group. Okay. If
Okay.
PPTs are also, I will share them.
Okay, ma'am. I
Okay.
think Darwinism is most important because it is like a mostly asked question, theory of Darwin.
Yeah. Yeah, definitely. Yeah, I will check once and I will share.
Okay, ma'am. Okay.